and Professor Dr. Nestor Daniel B. Fernandez. Dr. Nestor Daniel B. Fernandez. So these two keynote speakers will deliver the speech start from now, and we start with our Professor Dieter Schramm. The presentation will be 20 minutes, and then we continue with Dr. Fernandez. And then after that two session of 20 minutes, we continue with another 20 minutes for question and answer. So for all participants, I would like to introduce Professor Dr. Dieter Schramm. Is head of Department of Mechanical Engineering from University of Duisburg, Essen, Germany. Professor Schramm doing research in the field of mechatronic modeling and simulation, and also robotic and manipulator technology. So please welcome Professor Schramm. Prof, you can start the presentation now, please.
Okay, thank you very much. So, dear Mr. Chairman, the participants of today's conference, I'm truly pleased to have the honor to speak to you, although I cannot be with you physically today. By the way, I will be in Kuala Lumpur tomorrow, or the day after tomorrow. So my name is Dieter Schramm. I'm the head of Chair of Mechatronics of the University of Duisburg-Essen in Germany. And I would like to thank the conference committee for inviting me to present some of the results of our research. The title of the presentation is Aspects of Automated and Electric Driving on Land and Waterways. The presentation starts with a brief overview of some of the research areas that my chair has been working on during the last years, and then I will present some of our research results in the field of automated driving on roads. And this will be followed by an overview of our research activities in the field of automated and remotely controlled navigation of inland waterways. So what you can see here are the members of my team, of my chair team, and they did, we together did the work, and we try to sail together on the path of scientific progress, but also on applications. So the next slide shows a short overview. It shows a selection of research fields of activity that we have dealt with thoroughly during the last years. The slide shows two very different but methodically closely linked subject areas. On the left-hand side, the activities in the field of motor vehicles, starting with vehicle dynamics system. This was later on supplemented by the development and installation of dynamic driving simulators, but also by the establishment and use of models to simulate traffic flows with many thousand objects. And in addition, we also researched methods for robot-assisted automatic charging stations for electric vehicles. The right-hand side of the slide shows the activities in inland vessel automation, accompanied by the automation of loading processes in ports and new types of berth that are not necessarily part of a conventional port. At first glance, these two sides of the slide appear to show very different areas, but there are many similarities, and we will see that in a few minutes. I have just said that we are not only dealing with the simulation of the vehicles themselves, but also with the traffic flow that results when a large number of vehicles are moving on roads. This is the content of the next section, and therefore I would like to look into another research question very rapidly. How does automated driving affect traffic flow? Traffic flow and semi-automated driving would affect future traffic. So when considering the automation of motor vehicles, there is a standard categorization that has been established for many years, which is presented here. A total of 6 levels are distinguished. Level 0 describes vehicles without any driver assistance. Level 1 only provides assistance, and level 2 corresponds to assisted driving. And this is the state of the art in legislation all over or in many countries of the world. The highest development stage is level 5, in which a driver is no longer required. In particular, a steering wheel and a gas pedal are no longer required. This level is not approved worldwide on public roads. I would like to limit myself here to the difference between level 0 and 5. There are a number of other studies on this at our chair, which you can find easily on our website. So we are very much interested in the influence of automation on traffic flow in urban areas. And in this context, a traffic flow model of the city of Duisburg with around 500,000 inhabitants was created. We did a similar research with Chinese colleagues in Wuhan. It covers several hundred streets and can be simulated with tens of thousands of vehicles. We used a microscopic traffic flow simulation model that allows the vehicles to be individually equipped. This means that we can distinguish in particular between vehicles that are driven by human drivers and those that drive automatically. The difficult part of this description is not the highly automated driving, but a simulation of the human driver. And this is part of a doctoral thesis in which driver models based on artificial intelligence were developed as part of extensive test subject studies. Here again, I can only give one example of a result, maybe a second one on the next slide. In this case, we simulated an area of the city of Duisburg where we assumed the traffic demand would be 50% higher than at normal times. This means early in the morning and in the evening during rush hour. In total, over 30,000 vehicles were simulated in real time, and the model validation was fed with 76 induction loops, which were used to record the speeds and types of human-driven vehicles in real traffic today. This graph shows an evaluation of the average speed per day, and you can see that with level 0 vehicles, the average speed is significantly lower than with fully automatic vehicles. This is mainly due to the fact that the reaction time of human driver vehicles are significantly longer than those of automated vehicles. Similar results can be seen on the next slide, and here we calculated the time loss reduction of level 5 vehicles, and this added up to 34%. As I already said, there are no level 5 vehicles in use today, at least not on public areas. However, there are some exceptions. In test fields, it is possible to have vehicles drive fully automatically, and there are a number of systems for this. And one of these systems that we are currently investigating scientifically is the so-called flight system, which is being presented here. And the question is whether there is a way is another path to autonomous driving other than expensive conversion of conventional motor vehicles. And next question is there a meaningful, affordable, and individualized complement to public transportation? So maybe, for instance, replace trams and and coaches and so on. The principle of the flight system, which has been developed during the last year, is that it works with so-called virtual rails, which can be conductor loops laid in the road, but also can be simply be painted lines applied to the road surface. The idea behind this flight vehicle is to make much better use of existing road layout and road space than it is the case today. An important aspect is that, unlike other solutions, expensive sensor technology is not installed in the vehicles, but in the surrounding infrastructure. This leads to significantly lower costs overall. At the moment, there is not yet a fleet deployment of these vehicles, which means we are still working on a scientific basis of how such a vehicle can be meaningfully integrated into today's road traffic. To demonstrate what such traffic could look like, we have examined the planned construction of our new faculty campus on a site outside the city. This faculty campus is planned for 2030 or 2035. This virtual movie is intended to illustrate this, and the whole thing is currently a simulation. This means that this system and this operation with these vehicles has not yet been realized. However, we hope that we will be able to realize it in this area or in other areas in the future. So the next research questions I would like to present briefly. And this is as we have a group of people who worked on robotics, and Dr. Kurniawan was part of this team many years ago. We are also looking how to use robots to automate the electric charging of electric vehicles. And we have been investigating this question together with an industrial partner for several years now. And we then presented the results to the public a few years ago at the famous International Motor Show in Munich. On this slide, you can see the system. It consists basically of a robot, of a so-called cooperative robot, which can be bought at the market at the moment. And what we did is we added some cameras, some more sensors, and a lot of artificial intelligence in order to automatically find the charging flap, and this charging flap can be opened automatically, and the system is also able to remove the plug from the charging station and insert it into the vehicle. This is only intended to give a brief impression of the topics that can be scientifically investigated in addition to the narrower field of electromobility. It has always been important to us that these scientific results also provide impetus for applications that can then be used industrially. I would now like to proceed to the last part of the presentation, but this part is the biggest part of the presentation as well. And this part deals with automated or remote controlled driving on waterways, more precisely on inland waterways. You can see an example here in this picture. This slide shows an example of a typical inland waterway vessel during a reversing maneuver, and we try to do this automatically in the future or by remote control. And I was also asked, why do we do this? Because today we have these vessels, and normally there is not a big problem with them. But the reason for that is that the freight volume in Germany and other countries currently accounts for around 5% of the total freight volume, which corresponds to 205 million tons of freight per year. This short video shows two typical inland vessels on the River Rhine in Germany, and unfortunately, the proportion of freight volume on inland vessels has decreased during the recent years. And there are a number of reasons for that. So the number of 5% doesn't sound like much at first, but if putting this relation to transport by rail or road shows a transportation by water was considerably potential. This slide shows freight traffic at the German-Dutch border crossing at Emmerich am Rhein. Here, 108,000 inland vessels transport more than 150 million tons of goods per year. If we would like to transport these goods by train, we would need 3.8 million railroad wagons. This corresponds to 126,000 freight trains per year, and this means 345 freight trains per day. If you do that by truck, we don't need to talk about that, but it will end in a 300 kilometer long truck convey per day. So this makes not much sense. And this is exactly the reason why we also try to apply the experience we have from the automotive business to waterways. So waterway transport is environmentally friendly. It has a lot of free, unexploited freight capacity. But we have a lack of qualified new crew members for ships. And also there is a high age of currently deployed vessels. So we need also retrofit solutions. The solution for that, to meet these challenges, is automatization, because automatization mitigates the need for staff. It increases economy of smaller ships, which we will need in the future, and it can increase traffic safety. The question now is, how can the operation of inland vessels be automated? Can we use methods and technology from automotive industry? And what research facilities are required to do that? First of all, I have to mention that there is a big challenge of inland waterway transport because waterways are different from land roads. On the left side on this slide, you see typical waterway, which is not really comparable to a road because it changes its shape over the year and also during time over many years. On the right, we see the River Rhine, for instance, during a period of extreme drought. In this case, the water depth is significantly less than in other seasons. And now the question arises, how can we transport our experience from automotive science to waterways? And similar to motor vehicles, automation requires categories have also been defined for this sector. Furthermore, the state of art is comparable to the automation of road vehicles. Partial automation, according to level 2 in automotive, is already available and approved. Of interest for our research in this case, other than automotive, is to bring level 5 on the road, means in this case on the inland waterway. And so we work on full automation, and as a special case, the remote control of ships. So similar to motor vehicles, to conduct research in this area, corresponding test facilities are required, and this slide shows on the left an overview of our simulation and control center, which has opened in 2020. The right side shows an overview of our real-world test fields, and these consist of a 20-kilometer section of a shipping canal, as well as real inland vessels and facilities for tests with scaled models. The link between simulation and real operation is formed by a digital twin, which you see in the middle, and a virtual waterway. These facilities have been in operation for around 3 years now and form the basis for our research in the field of inland navigation. The digital twin is key to do all this research, and we developed a digital twin which is simulated in real time, and it is based on a simplified flow model that nevertheless represents reality accurately enough. This you can see on the right side. There's a simulation of a typical inland waterway vessels with high waves, of course. One of the first projects we did was Autobin, and Autobin was about autonomous inland waterway vessels, and the ship guidance from start to destination should be fully automatically. This means we need a self-driving system without any human intervention. Collision avoidance, of course, is key with other waterway users, shore and objects, and it should, of course, comply with all given inland vessel traffic rules in order to get it approved by the legislation. So we want to reduce control tasks for the crew, meaning reduce also personnel costs, prevent accidents due to human error, increase safety levels, and the final target is fully driverless operation. And we use this knowledge, we use a lot of knowledge from autonomous road driving because the basic tasks are independent of the system, and autonomous driving methods and sensor concepts can be adapted. This is shown on this slide here, and all these sensors which you can see here are also in use in high-equipped cars, for instance, in Mercedes cars and others as well. So we talk about LiDAR, we talk about mono and stereo cameras, we talk about GPS, radar, and so on. And so it's very, very similar. On the way to autonomous driving, we also talk about remotely controlled driving in inland vessels. And this is shown in this short video. So we talk about remote control of inland vessels, and we have a real test vessel complemented by a digital twin. You just saw these test vessels going to the water. Sensor technology to measure movement behavior on the test vessel was installed. And we also did some training of the ship's command personnel, and the target investigation, evaluation, and optimization of human-machine interaction was done in cooperation with our staff. Here you can see a real view in the real world on our test ship. Yes, and I can say it worked very well. And the next and last step, I hope I keep the time, maybe. So along with the automation of ship operation, it also makes a lot of sense then also to automate the loading of inland vessels, as it is already the case in large overseas ports. But this is not also the case for inland vessels. So new approaches are being pursued to enable the automated operation of small ports on inland waterways. For this reason, we started to set up a test center a few years ago for innovative port and cargo handling technologies. This center opened a few months ago. The center offers a range of innovative development opportunities. This includes a test hall, fully automated port operation in the scale, and that's important, a scale 1 to 16. So it's a rather small building. So this slide shows a virtual insight into the operation of the port research laboratory. The real laboratory was opened and presented, as I said, to the public a few months ago. Okay, so this is it more or less for this presentation, and I think I kept the time more or less. And I would like to conclude my presentations with a look at our research vessel that has just been designed and ordered together with our partners. And this ship can navigate automatically and will be electrically powered by batteries and also by fuel cells. It will also provide workplaces for at least 7 researchers. And at the end of this presentation, I would like to thank you for your attention. And if there are any questions, I will be glad to answer them. Thank you very much.
Thank you very much, Prof. Scrum. Very interesting presentation. Now we move to question and answer before we proceed to the second speaker. Any question from the floor, please? Yes, Prof. Kamal.
Hi, Prof. Shram. I'm Kamal from University Kebangsaan
Very
Malaysia.
interesting presentation. Now we move to question and answer before we proceed to the second speaker. Any question from the floor, please? Yes, Prof. Kamal.
Hi, Prof. Shram. I'm Kamal from University Kebangsaan
Very
Malaysia.
interesting presentation. Now we move to question and answer before we proceed to the second speaker. Any question from the floor, please?
Am I online? Can you hear me?
Hi, Prof. Shram. Okay, I'm
maybe
Kamal
there's
from University
Very
Kebangsaan Malaysia.
interesting presentation. Now we move to question and answer before we proceed to the second speaker. Any question from the floor, please?
Something that am I online? Can you hear me?
Hi, Prof. Shram. Okay, I'm
maybe
Kamal
there's
from University
Very
Kebangsaan Malaysia.
interesting presentation. Now we move to question and answer before.
I could hear you, but can you hear me? Can you hear me? Can you hear me now? I can see you, but I don't hear anything. Can you hear me now?
Yeah, I can hear you.
Yeah, could you repeat your question, please? Because I did not catch it. There was a disturbance and frequent repetition. Can you hear me now?
Yeah, I can hear you. Okay, Prof. Shram. My first question.
Yeah, could you repeat your question, please? Because I did not catch it. There was a disturbance and frequent repetition. Can you hear me now?
Yeah, I can hear you. Okay, Prof. Shram. My first question.
Yeah, could you repeat your question, please? Because I did not catch it. There was a disturbance and frequent repetition. Can you hear me now?
Yeah, I can hear you. Okay, Prof. Shram. My first question.
Yeah.